flux. Do you remember those little lines we were drawing last chapter? We were drawing little lines. So we drew this little line. We've got a charged particle. Oops, it's not going to work. We've got a charged particle, and I've got these little flux lines coming off of it. Flux is the total number of lines passing through a surface. Okay? So if my surface is here, like this, right? If my surface is like this, I would say how many flux lines are passing through that surface? What's my flux? 2. Okay? Now, we can make it trickier than that, but we're talking about Faraday, right? So we're going to have things that just like, okay, 2. That's the game we're playing here. Okay? Faraday said, hey, do you remember what flux is related to, by the way? Electric field, how?
It determines how it would go in an electric field.
How we go in an electric field. Also, what else about the flux lines?
Like its strength, right?
The strength. The closer, the more flux lines you have per unit area, the stronger the electric field, right? So if flux is the total number of lines, I don't know what you guys are looking at, but if flux is the total number of lines, then flux per unit area must be what? Electric field. Now, on first blush, I want you to look at that, and that makes perfect sense, because the closer the lines are, the better electric field. But remember, what are these lines? We made them up. That's a little disturbing.
Is that technically like an infinite amount?
Well, it depends on how many we drew, right? It seems kind of odd that we're now going to say, well, that's the number of lines I draw is the electric field for that area. So we're probably going to have to, in some way, standardize this number of lines, so we can actually get an electric field that's measured in newtons per coulombs. Okay? Does that make sense so far? Now, playing with this just a little bit, I'm going to go ahead and move the A over here. I'm going to say the flux is equal to the electric field times the area. Got me so far? All right. So here's what I want you to do. It's problem. It's the next problem now. It says, let's say the uniform electric field of 2 newtons per coulomb. You see where I am? Let's say the uniform electric field of 2 newtons per coulomb is directed in the positive x direction. What is the electric flux through the square perpendicular to the axis that is 2 meters by 2 meters? Everybody take a look at this problem, think if you can think how to do this problem, and then try it out. Tell me how much flux I have. How many lines of flux do I have going through that particular surface area that's 2 meters by 2 meters? Well, what's the area formula of a rectangle? It's this.
Oh wait, no, that's right.
Rectangle. That's a triangle.
No. I was looking at the triangle before. All right, let's just move on.
So I got a square perpendicular like this.
Two.
I've got 2 newtons per coulomb going through it.
Spoiler alert, Jason.
So my electric field is 2. But that's the problem. I got to try. Okay, I got electric field going this way. I've got a 2 by 2 rectangle sitting in front of it like this.
Like that.
How many flux lines would go through it?
1, 8, 7, 8, 2.
Electric field is 2. The area would be what?
4.
2 times 2, or 4. So my flux lines would be 8.
7. Also, there's 8 flux lines.
8 flux lines. But we're not going to write 8 flux lines anymore because we're going to be more technical than flux lines. We're going to say 8 newtons per coulomb times meters squared. Apparently a flux line is a newton per coulomb meter squared. Yes.
Wait, can we just put the meter square on top?
Yes, we can. Now, this gets worse, so you got to pay attention to this next little bit because this is something that last year people struggled with all friggin' year, and it's not that hard. You can do it about 15 different ways, but you just have to get it one way right. Anybody notice that I slid a little dot in here? If things were coming at an angle like this, there would be less flux lines traveling through that. Okay? Because they'd be going in a slant, there'd be less flux lines. Also, by the way, the flux lines would have less effect. There's another way to look at it. We're talking about what an electric field actually is. So the more perpendicular, the more lines would go through it. Agreed? Now that means we should use a. Yes.
Why though? Because if you slant them.
Okay, here we go. Here's my arrows. I'll go completely this way. How many flux lines do I get? Maybe. If it's an infinitesimally skinny thing, you get none, right? So don't I get less because my shape is not pointed the right way? And the more my shape's pointed towards perpendicular, the better off I am. Agreed? So the more perpendicular, the better off I am. Now, what's wrong with the dot notation, Mr. Beeble?
It has cosine.
It has cosine. That is to have cosine on it. Absolutely has cosine on it. Why is that surprising?
Because when you take the angle,
Yeah.
the perpendicular vector should be sine.
So it should be sine. So something's wrong with what we're doing here. Or right with what we're doing. We just don't know what it is yet. So here's the problem. Way back when, back in trigonometry land, I told you that the area is a cross product. If I do length times width, way back when in grade school, they casually wrote that as an X in the middle. And that means that every third grade teacher thinks that actually means multiplication, but it means a cross product. And if you do the cross product correctly, I get 2 times 2, which is 4, but I also get a what? I get a direction, don't I? And if this is length, and this is width, sorry, that's length and that's width, then my direction for my area vector would be right-hand rule, curl my fingers, out of the board. So an area vector is either out or in.
Wait, what is an area vector? What does that mean?
That's a good question.
What? An area is like a dimension.
Yeah, but try living underneath the dirt. There's a difference between up above and below it, isn't there? Always has been. You prefer the top part than the bottom part, don't you? At least for living. Now, if you're gold mining, living down below would be better. Okay. So, back one step. If I'm doing an area vector, that's either this way or this way. And that's why it's a dot product. Because we want that which is in the same direction, right? Is strongest. Now, we're physicists. This dot is a mathematics thing. If you are perpendicular, you are strongest. If you are parallel, you are weakest, right? And so you're going to look at the picture and use whatever sine or cosine you need to use to make it so perpendicular is strongest. Does that make sense? You're going to take the component that's in the same direction. So if I give you a vector, if I get a vector field like this, and I give you that this is sitting at, it's a terrible example because it's exactly what I did on the example problem I'm going to give you in a moment. So let's do this instead. Let's say this is at 45 degrees. 45 is terrible because I don't do sine or cosine. Let's make it 30 degrees. So it's even flatter still, right? So I'd have very little electric field going through there, right? So my component in the same direction would be this component here, would it not? So what would I use? This is the perpendicular component, isn't it? Which is stopping my electric field. This is the only part that can stop my electric field. It's this component here, right? So what do you use, sine or cosine?
Sine.
Sine, because that's the opposite side. The perpendicular is the opposite side. Does that make sense? So I go electric field times the area of this shape times sine of 30 degrees. I have to get the perpendicular piece.
Mr. Ray.
Yes, sir.
I'm still confused about the area vector. This obviously makes sense for like
Okay.
underneath or above the dirt, but why would it matter for a plate?
Because here's the stupidity of the whole thing. We're in it. This is a math equation, is it not? So they know this is a cross product. It's got a vector to it. And that vector is going to be, if this is your plate, that way or that way. And so therefore they chose a dot product. Mr. Beeble over there looked at this and said, wouldn't I do sine of 90, not cosine? Dot product says use cosine, right? Blindly use cosine. But because you have an area vector here, the area vector is this way, they're in the same direction, aren't they? So since they're in the same direction, I should use a dot product and use cosine of 0. Now, we're physicists. This dot is a pain in the neck. Because people think about it and they go, oh, I'm going to use a cosine. No. Our first example, we end up using a sine. You want that which is perpendicular to the electric field, right? So you're going to drop that in the perpendicular. You're going to look at the picture and go, is this sine or cosine in this picture? Sometimes you use sine, sometimes you use cosine. Whatever makes it perpendicular to the electric field coming at it, that's what you're going to use.
So when would we use cosine? Like to make
If I did this instead, if I said this is 60 degrees, I still need to do the perpendicular, but now I'd be using the adjacent side of the cosine.
Okay, cool.
That make sense? Good. Let's try out, there's a problem on the bottom to ask this question right here. It says, let's say there's a uniform electric field of 2 newtons per coulomb directed in a positive x direction. What is the electric flux through the square angled at 120 degrees with the x-axis that is 2 meters by 2 meters?
What is that? The thing, the notation for electric flux. What letter is that?
It's an iota.
Oh, like.
It's very similar to inertia, rotational inertia.
Yes. So is this just like
What? I think it's a baby. I think it's a baby one of these.
Wait, the inertia one?
No, the inertia is this one. I think the one for flux is they use the baby one. I also must admit that after a while, physicists do things similarly until they start to look like inertia, rotational inertia. You'll find that most physicists just use an eye, they don't bother with a little circle in the middle. And most people doing flux just draw this with a line through it. They could be the same letter, just with time. You know, I showed you ohms, right? It's like a girly hair. It's not. It's a dunk, 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 round circle, dunk, dunk, up. But nobody does that. I mean, nobody. Not even the textbooks do that anymore.